Hello, y'all. Welcome to lesson 141 of my DP chemistry curriculum. Today we're doing structure 3.2.12. This is an HL topic, and this is also the last video of this entire curriculum. So with that said, we're going to take data from different techniques and combine them in structural analysis. So we're going to interpret a variety of data, including analytical spectra, to determine the structure of a molecule. Basically, we're going to take our last three videos about IR spec, mass spec, and HNMR and combine them so that we can analyze individual molecules and try and figure out what they are. So with that said, let's just jump into it. We're just going to do a couple examples here, and that's going to be the whole video. So let's start with a compound that has an empirical formula of C3H6O2. Now we can get empirical formulas from X-ray spectroscopy, which gives us the percent mass of each element, and then we just divide and do the moles per each and so on to get our empirical formula. So now that we have that, let's go ahead and look at a mass spec of this compound. So we notice a couple things. First, we're going to go ahead and find out our actual molar mass, which we can look at the furthest to the right peak minus the n plus 1 peak, or sorry, not n plus 1, mass plus 1 peak. And so that's going to give us a molar mass of 74. So that's going to help us identify the compound, which coincidentally, C3H6O2 also has a mass of 74, meaning our our molecular formula is the same as our empirical formula. Then we're going to go ahead and start doing some fragment analysis. Generally, we look at the largest peaks, the most common fragments. So that is MZ of our base peak, which appears to be about 29. And we'll do another fragment analysis of mass at 45. So for 29, what we're going to do is take our mass, which is 74, subtract 29, and that will give us our neutral fragment of 45. We'll do the same thing over here for 45, which is 74 minus 45, giving us our neutral fragment of 29. So we'll go ahead and use our data booklet, which I've got up right here, to identify those fragments. So I noticed right off the bat that my fragment of 29 is either CHO or CH2CH3, and my fragment of 45 is our carboxylic acid, COOH. So our neutral fragment is going to be COOH, and this is either going to be CH2CH3 or CHO. So we have already brought this down to some type of carboxylic acid for sure, and either some type of alkane or aldehyde. So that's about as far as our mass spec will take us. So from there, we're going to move on to our infrared spectroscopy. So for this compound, we have this nice IR spec. And I'm going to bring our attention to two specific peaks. We'll do this peak at 1750 centimeters inverse, and we'll do this larger peak at around 3000 centimeters inverse. Now remember, everything before or after 1500, depending on how you want to look at it, is the fingerprint section, and we're only analyzing the functional group section. So 1750, looking at our chart here, is going to be aldehydes, ketones, carboxylic acids, and esters. So we know that this is the presence of a C double bond O. And then 3000 generally represents our carboxylic acid, specifically the hydrogen bonding. So this is going to represent COOH. It's specifically the OH bond within COOH. So once again, IR spectroscopy now gives us extra confirmation that we do have a carboxylic acid. All right, moving on to the final analytical technique, HNMR. And we'll go ahead and look at that here. Now in HNMR, I noticed four peaks, but always remember our furthest right at zero is our TMS peak, and so we can ignore it. And within those, we actually have three peaks. So I'm going to note that there are three chemical environments. Basically, that means we have three different protons. Now, this is a high-res HNMR, so we also get some splitting. But before we go through that, let's just go ahead and take the low-hanging fruit of this peak all the way that's downfield. A downfield proton is generally going to represent an OH bond. Now, this is so downfield, being at like 11.8, this is likely something that has to deal with a carboxylic acid. Remember that oxygen really shifts it downfield. You can see that when you have hydrogen near an aldehyde, it'll be a more downfield shift. So this is going to likely be an OH from a carboxylic acid, confirming what we kind of already know. All right, so now let's go to our splitting and see what that tells us. So I notice that over here we have a singlet, which just more confirms the OH theory, as that hydrogen doesn't really get interfered with or doesn't participate in splitting patterns. Then at about 1.2, we have a triplet, meaning it's close to CH2. And at 2.4, we have a quartet. So putting all of this down and knowing that our molecular formula is equal to our empirical formula, there's only one real thing it can be. We definitely are going to have I'll just do a big therefore. We're definitely going to have a C, double bond O, OH. Everything's confirmed we have a carboxylic acid. Then, because we have three different environments, we need two more carbons. Each carbon's going to have its own environment. And kind of judging from what we saw in our mass spectra, plus now um, assisted with our splitting patterns, it's got to be propanoic acid. Because if we look at this, this is one group, and that would have a triplet. So those hydrogens represent that peak at 1.2. These hydrogens represent that peak, that quartet over at 2.4, with lastly this hydrogen representing that peak at 11.8. So this is going to be propanoic acid. So we've just used analytical techniques to figure this out. So we're going to do one more example, and I'm going to give you all the information right at the top. Our new empirical formula is C3H6O. I'm also going to give you, I'll move this all to a new page so it doesn't get cut off. I'll also give you the data booklet, or you should have your data booklet on you, but I will give you all the graphs at once. So go ahead, take a moment to pause this and try and figure out what this is. So try and figure out the entire compound from the information given. You can go ahead, uh, pause it, and go for it. Otherwise, I'm going to get started in 3, 2, and 1. So for mass spec, right off the top, it's always good to find that our mass, and this is 58, which coincidentally, again, that is the same as our empirical formula, which means our molecular formula and empirical formula are the same. Then I'm going to go ahead and look at the base peak. I think that's always the easiest one to look at. Very obvious. Right here, our base peak has a mass of 43. So 58 minus 43 is going to give me 15. 15 from my data booklet is likely a CH3 neutral fragment. So I know I'm going to have an alkyl fragment as part of my entire thing. And not only is it there, it is incredibly common. This, something you can learn later on, means there's likely more than one possible alkyl fragment if it's that common relative to everything else, meaning that this may have more than one CH3 that can be bumped off depending on the pattern, the fragmentation pattern. All right, moving over to IR. Again, 1500 we'll ignore. So I'm going to look at, and I'll change colors for IR, just make this a little easier. So we'll ignore 1500, and I'm going to immediately go to that 1750 peak, which I have begun to recognize is a C double bond O, some type of carbonyl, meaning an aldehyde or a ketone or carboxylic acid. However, this is not some band spectrum, so I know it's not carboxylic. Also, I know it's not carboxylic because it has two oxygens, and we've already discovered that we only have one oxygen in our compound because our empirical and molecular are the same. So this must be an aldehyde or a ketone. All right. So knowing it's an aldehyde or a ketone really helps us out as we go into HNMR. We have our TMS, and I'll change colors here to something more visible. And on top of our TMS, we only have one chemical environment, meaning that all our hydrogens look exactly the same. So bringing all this together, I know that we have three carbons. It's C3H6O, and we have either an aldehyde or a ketone. The aldehyde would look like this. And the ketone would look like this. So one of these has three chemical environments, while the other, using a plane of symmetry, is shown to only have one chemical environment. So our compound must be this one on the right. This is propanone. So that's it for combining analytical techniques. I hope this helps you understand how we can use these methods to identify species. And have a great day, and I hope you enjoyed all 141 lessons if you're HL or far fewer if you're SL. Thank you for watching.